Hello, this is Susie Luhan, and this is the one about partial differentiation and also introducing Cobb Douglas functions. So the very famous Cobb Douglas production function, there it is. Q, output, is a function of labour and capital. This is a very simple version of the Cobb Douglas, and we recognise a Cobb Douglas because these are all multiplied together and the L and the K both have powers less than 1. And there must be less than 1 because each in its turn has diminishing returns. Now the early ones you will see in your economics career will have powers that add to 1 because you start off by looking at production functions which have constant returns to scale. So that's the kind of Cobb Douglas we're going to be looking at today. So we're going to start by doing some rearrangements because you get some nice insights out of a Cobb Douglas function. For instance, we might be interested in Q over L. Q over L will be average product of labour. We take the overall output and divide it by our number of workers and we get an idea of the average output per worker. Output per worker, labour productivity, average product of labour, call it what you will. We also have average product of capital. Again, Q divided by units of capital, so we can see how much output we're getting for each of our units of capital, millions, thousands, whatever they are. All right, so how can we interpret L over K? L over K tells us the amount of labour we have for the amount of capital. So if this is high, it's a high labour to capital ratio. Which one does that look like? Well, it looks like this one, doesn't it? We've got a lot of labour units for relatively small capital. But if this goes down, we're sort of veering more towards that environment. And vice versa, we've got capital to labour ratio. You can see these are just inverses of each other, one over the other. So if we have high capital labour, it's looking more like this environment, isn't it? Where for every head of worker, can't even see a worker there, for every head of worker we've got a lot of capital invested. So big K over L means high capital intensity. So those are terms that we're going to see later. So just by rearranging our Cobb Douglas functions, we can get some insights about this. So let's look at the Q over L, which is average product of labour on this side, and do some sort of algebraic rearrangement. And we've learned, haven't we, that if we divide one side by something, then we must divide the other side by it, and then everything stays nice and balanced. But before we do this, I need to remind you of some basic stuff about powers. And here it is. If we have a variable L, say to the power of 5, divided by L to the power of 2, because L's are both the same, we can just subtract the powers. If we're multiplying, we add the powers. If we're subtracting, we subtract the powers. So we can see that this is L to the power of 3 because we can just subtract those powers. But what if we've got so if we subtract powers this time, we're going to have 2 minus 5, and we're going to have L minus 3, and hopefully you will remember that if the power is negative, it rightfully belongs on the bottom. So there it is. Okay, now it's going to work, it's going to be a little easier for you if you could do this a different way for what we're about to do. And let's say this time we're going to bring that L squared down to the bottom. So here's the L5, it's already there. We're bringing the L squared down, but to put it on the bottom it has to be negative. Now these two are multiplied together, and when we multiply two variables with powers together, we add the powers. So 5 plus minus 2 is L to the 3. So you see we get there quicker, and sometimes it is better to do it this way. So back to this. Right, so we've got L on the top and L on the bottom, so we know we can put those together. So here's my L, that was already on the bottom, and every number really has an invisible power of 1, but we don't normally write it, but I'm going to write it today. And we're going to bring that L to the 1/5 down to the bottom, but when we bring it down to the bottom, it gets a negative power. Remember, a negative power means it rightfully belongs on the top, or if it's already on the top, it belongs on the bottom. Right, so now I can do k to the 4/5, and now I'm going to multiply these together, which means adding the powers, and when I add these, I'm going to get L to the 4/5, so these powers are now the same. All right, so, and because, so I can write this k over L, because if top and bottom of a fraction have the same power, the whole fraction has that same power. So there we go. So this is quite an insight. This tells us that the average product of labour is a function of, can be derived from, is a function of a constant, but also the capital labour ratio. And that makes sense, doesn't it? If we think about how productive each labourer is, or each member of staff is, it's going to be a product of how much we invest in them, so how much capital to labour there is. Let's have a look at this one. This time let's do average product of capital. So I've got 8, L to the quarter. I've got my k that I put on the bottom because I wanted to divide by k. I'm going to bring this k to the bottom and make the power negative. So this will equal 8L to a quarter over, and now these two are multiplied together, so I add the powers, so this is going to be k to a quarter, and because those two have the same power, I can put them inside one fraction in brackets and put the power outside. So I see that the average product for capital is a function of another variable, really, L over K, which is the labour to capital ratio. So productivity we get from capital depends a little bit on how much, on whether we're supporting capital with some amount of labour. Okay, so how about these ones? These powers are not numbers, they're symbols, but economists use these a lot because they like to make some sort of general observations. Now here we are going to assume that constant returns to scale. Constant returns to scale tell us that these two powers add to 1. These two powers add to 1. So bear that in mind. So let's make this Q over K this time. So we're looking for average product of capital. We're dividing by K. We're going to leave the L on the top, and we're going to, there's our K. Now we put, because we're dividing by it, and we're going to bring the K to the beta down. In order to do that, we've got to make beta negative. Now we're going to multiply these two together, that means adding the powers. So we're going to end up with 1 plus minus beta, 1 minus beta. Ooh, but that's okay because of the constant returns of scale. We know that alpha plus beta equals 1. So alpha is 1 minus beta. Has to be. Economists do this all the time. You have to keep up with them. L over alpha equals K over alpha. So we're getting the same result as we did last time, that average output of capital is a function of the labour capital ratio. So let's do this one. Let's make this one. This time we'll find the average capital, average product of labour. Oh, I didn't mean to write that, but never mind. So it's equal to, so we've got our little power of 1 there, because it helps B anyway. We're going to leave the K on top, and here's the L that we're dividing by, and we're going to bring that L down, but if we bring it down, we have to make the power negative. So we're now going to multiply these. So that means adding the powers, so we have L1 minus alpha. These now have the same power, so we can put it into a single fraction. And we can simplify this if we want and say it's beta, because alpha plus beta is equal to 1. So again, we've got the average product of labour is a function of the capital labour ratio. Now, because the Cobb Douglas is a multivariate function, it's got two variables, it's a function of k and l, then it means it has some lovely graphs, lovely three-dimensional graphs. So if you could just imagine for a moment, this is a three-dimensional graph of labour and capital, and overall it's Q for output, the production function. And the idea is that if we think of capital as a fixed amount and just think about labour, then if you can imagine looking at this graph, you can see that it has the traditional diminishing returns. Now, that's what it would look like. We'd be looking directly at this shape. On the other hand, if we held labour constant, imagine looking at it from this angle, from the capital axis, you're also going to see another one of these traditional diminishing returns shapes. Just a final note on this. This is a simplified production function with just one variable, and I just want to show you what it looks like when something's raised to the power of a number less than 1, for instance like a square root, as this one is. So this is what it looks like. It's our old diminishing returns. But if we have another function, which might be one of the ones we've just found by rearranging our Cobb Douglas, then we've got the average output of labour is a function of capital labour ratio, and we can plot that, or we can do a quick and dirty sketch really easily. So just like here, we've got Q over L. Instead of Q, we've got Q over L, and on this, which is a function of this, our independent variable, which is a capital labour ratio. So we can easily render this into a graph. It's just that diminishing returns shape. Just be careful how you label the axes. So because the Cobb Douglas function is a multivariate function, two variables, k and l, if we want to differentiate it, which economists do a lot, then we need another sort of differentiation that we haven't done before. So here's us taking another step up, and this is called partial differentiation. And here's a definition, I think. The idea is that we can differentiate with respect to one of the variables and behold the other constant. And then it is quite straightforward. And we're going to get a little practice of that. So, but before we do that, a little notation. So here's a Cobb Douglas function. And so dq by dl is a partial derivative of that. So the partial means I have differentiated it, but I've held one of the variables constant and used the other one to differentiate. And because it's different, we have a slightly different symbol for dq by dl. You see the curve d. Whenever you see the curve d, it tells you that there's another variable somewhere in the background that is being held constant. Okay, this tells you that this is a derivative of a multivariate function. Here's some very basic ones. So let's get a little bit of practice with partial differentiation. And hopefully, as I do it, you'll see what we're talking about. So I have a function of z, is a function of x and y. So it's a three-dimensional sort of shape. And we've been asked to find dz by dx and dz by dy for both those two functions. So let's jump right in. So d, curly d, z over dx. Now, I just go through and I differentiate x like I always do. And whenever I come for a y, I treat it like a constant. So if I see a y, I don't differentiate it, I just treat it as a constant, which means if it's all on its own, it goes away in differentiation. So let's have a go. So I differentiate x as I normally would, so power times the coefficient. Now this is a function of y, so I'm considering y a constant now. So like any other constant, it goes away when I differentiate. This is going to go away when I differentiate, and this is going to go away when I differentiate. So this differentiates to just that one term. So here's dz by dy now. Okay, so I'm differentiating with respect to y and holding x constant. So this is now a constant, so it goes away. This is now something I differentiate, so multiply power by the differential, by the coefficient. Oh, it's both got powers of 2, so I should have put them together really, shouldn't I? Minus 4y, and the 5 goes away. That was a bit dopey of mine, so that's really simplifies to 8y. So now let's do this one. So I'm going to differentiate with respect to x. So that's a constant, that's a constant. I differentiate this as normal, so 2 times minus 3 is 6x. I differentiate that as normal, 24x, and that's a constant, so it goes away. So now let's differentiate with respect to y. So constant goes away. I differentiate this as normal, so 2 times minus 9 is minus 18y. That goes away as a constant, that goes away as a constant, so I do need to differentiate that. So half times minus 8 is minus 4, and I drop the power by 1, half minus 1 is minus half. So now we get to the exciting bit, differentiating Cobb Douglas functions. And again, we have to use partial differentiation because we've got multiple variables. And this time we're going to get some quite meaningful things. When we differentiate Q with respect to L, we're going to get the marginal product of labour. No longer the average, we get the marginal product. Remember, marginal is always the output of differentiation. And when we differentiate with respect to K, we're going to get the marginal product of capital. So we're going to get really quite meaningful things here. So let's go for dq by dl will equal, right, so here we go. So A and K will just be kept constant, but L we're differentiating by, so we're going to multiply by that power, so we'll tuck it in at the front if we want, and then and the L had a power of a half, so when we subtract 1 from it, we get minus a half. Now, the kind of thing we've been doing where we've been manipulating the powers, hopefully you can see that this can be simplified as, in fact, I'll put the A over the 2. I can bring the K over the L because they've got the same power. I'm going to bring that down to the bottom and make it positive, and because they've got the same power, I can put it together into one fraction. And so we get another insight that the marginal product of labour is a function of the capital labour ratio. Let's get dq by dk. So this time I'm differentiating with respect to k, so I'm keeping the A and the L constant. So I'll put the L first. Right, and now I'm differentiating my k, so I have to multiply by the power of k and subtract 1 from the power, which is going to be minus a half. And hopefully you can see that this will end up being A over 2 L. This has got a negative power, so it goes to the bottom. They will then have the same power, so I can put it in one fraction like that. And again, we see that the marginal product of capital is a function of the labour capital ratio. All right, let's do one more. dq by dl is going to be, here's my constants, A and K to the third, and L has got a power of 2/3, so I need to multiply by the power and drop the power by 1. So that will be 2A over 3 K over L. Hopefully you can see that L should come to the bottom. Let's do dq by dk. So A and L are constant, so I can just write those in. I've not left room. But now I'm differentiating with respect to k. K's got a power of 1/3, so I need to multiply by the power of 1/3 and drop its power by 1. See, the order doesn't matter. I've now put k at the end, but it doesn't matter at all. And hopefully you can see that that's going to be a over 3 L over k 2/3. Okay, so just this last one now. I'm going to differentiate q with respect to L. And that means 3 and k are going to be held constant, so I can just write those in. And then I'm going to differentiate with respect to L, which means I'll multiply by L's power and then drop L's power by 1. So let's say we want to bring L to the bottom. We could bring k to the bottom if we want. It depends on what inside we want. But let's say we're going to bring, I'm going to reverse the order because it always looks nicer when the number is before the letter. K1 minus alpha. And we're going to bring L to the bottom, which means we have to make its power negative. We stick a minus in front of it. So that's the same as 3 alpha k to the 1 minus alpha over L. So everything inside the brackets gets a minus, so it's going to be minus minus 1 becomes 1, and then minus alpha. And you think, oh great, the powers are now the same. So that is 3 alpha. Because the powers are the same, I can put them as one neat fraction. And then you will also remember that because alpha plus beta equals 1, then 1 minus alpha equals beta. So if I want, I can simplify that to beta. But economists will play around with it in all sorts of ways. I just wanted to give you an insight for that. Anyway, I hope that's helpful.